Okay, any questions about last time? Does anybody have any questions from the material last time or any questions about the class? Yes.
Quick questions. It had a resistor in it, and were we supposed to be able to solve it with the resistor or not?
So was that the question about the current?
Yes.
And what the current was? Yeah, we'll address that one. So if you took the attendance quiz and it had that question on there, I actually removed it after the class. And then if you want to retake it and refresh, it should be, the problems should be more of what you could do. So I'll address that today. So by the end of today, if you don't understand how to do that type of question where you look at a circuit and say, what is the current in this circuit just by looking at it, when you have a fixed current source, stop me and I will go over that again. Okay. So structure-wise, again, you're going to take the attendance. If you have just been added to the course, make sure you take that attendance from Monday, so you are responsible for that material. It will be due by tonight, so I decided to give it a day for those that might not be here physically and need to take that later. So I suggest I'll give some time, hopefully this time I'll give some time at the end of the class period for you to take that quiz here. So if you do want to bring your own laptop or iPad and have that ready, you can take that here in class, or you'll have time till the end of the next night to be able to do that. So every day that we have class, you'll have that attendance quiz, and then on Fridays, by the Friday night, the quiz will be due for that week. And so this one will be open Thursday morning till Friday night. You will need to do it. So some of the material on that won't be ready, or you might quite know how to do it until after the lecture on Friday, so you might need to wait till Friday night. The Unit 1 practice problems are always going to be great to help you. For this section, it's Unit 1 practice problems. Next section, it will be Unit 2 practice problems. Those are going to be great to help you to assess, like, are you knowing the material, and use that one because you can repeat that one as many times as you want. And then the quiz itself, you can only take one time. So that's your main score to say, like, yes, I am mastering this material. All right, any questions about any of that structure? You guys ready to tackle some more things? Okay. On Monday and Wednesdays, wrong one. So going forward, this Monday we'll start. There's going to be a review session. It will be 11:30 to 12:30. I think it's L122. An announcement will be sent around as far as the location of that one. And then after that, it will be every Monday and Wednesday. There'll be a problem session. From that 11:30 to 12:30. So if you want to work that into your schedule, that will be where you'll just look at problems only in that one to help make sure you're ready for the exams. Okay, so today we're going to continue on. We ended last period on the voltage. So we will continue on with the voltage concept and then also move into resistance and understanding resistances, and then identifying circuit components, and then parallel versus series. And then we're going to start looking at some nodes and what a node is in a circuit. Along the lines of that, we're going to go back and touch on a couple things like looking at the current source circuits and being able to say what is going on in this circuit. What is the current? Is that given to me? What is the voltage in this circuit? And how do I decide on that? All right, so voltage, we're going to maybe not.
Than anything, and it's they don't believe how toxic this is. If you're still using a plastic or wooden cutting board, you need to hear this. I never post stuff like this, but I had to share. I cook almost every day, so we've gone through our fair share of cutting boards. For years, we used plastic until I read about microplastics ending up in your food. One study
Okay, well,
even
let me skip this. This is annoying.
linked
Okay.
them to cancer.
Seriously, it won't let me scroll over. Let's see. Can I make it? There we go.
It's really all your choice as the circuit maker or designer or whatever. Usually we denote ground as the lowest potential in the circuit, but honestly, ground just means a common reference voltage. And the reason for this is because there really isn't such concept as an absolute voltage level. Voltage is always relative. And whenever we measure voltage, it's with respect to something else. That's why with your voltmeter, you need a red and a black wire. It's because you're measuring how much more potential energy is at the red point than the black point. Now, this may seem like a really subtle difference, but it's important. Now, say you have a 9-volt battery, for example. It doesn't mean that this pin is 9 volts and this pin is 0 volts. All it means is that this pin is 9 volts higher than this pin. And this is also why we can daisy chain batteries together, which is called putting them in series. Putting batteries in series wouldn't make sense if we thought about the one pin being 9 volt and the other pin being 0 volt. And the reason for that is because if we wanted to put them in series, then the 9-volt battery, 9-volt pin would come in contact with the 0-volt pin, and there'd be sparks, and the battery would probably explode or whatever because of the potential difference there. We get a short circuit. But none of that happens. So if we think about it the right way, which is that what we're doing is that there's just a 9-volt potential difference between these two terminals, then it makes perfect sense to daisy chain these batteries together, because then you're just adding up this 9 volts of potential difference across each battery. Okay, so let's get back to ground. Now, what we call ground in that circuit is a completely arbitrary choice. It just means that in your schematic or in your voltmeter, when you read 5 volts or you want to measure 5 volts, you're putting your black probe at ground. And that's why ground is important, because there is no such thing as absolute voltage. It has to be measured with respect to something. And how do you know what you're measuring with respect to? How do you know what your reference point is? It's ground. Now, when we made our inverting amplifier, which you guys can check out here, we set ground to be the halfway point between our highest and lowest potential. Now, we did this so that we could have a positive and negative supply for amplifying the positive and negative portions of our input wave, respectively. Now, let me demonstrate what I mean by this with some 9-volt batteries. With one battery, we can see that we have a 9-volt difference between the positive and negative terminals. Now, if we set ground to be the negative terminal, then this becomes a positive 9-volt supply, and we can check that out with our voltmeter, because with respect to ground, this is a positive 9 volts. On the other hand, if we just flipped it around, then we would have a negative 9-volt supply, because we could set our ground to be the positive pin, and that would mean that the negative pin is now 9 volts below the voltage of the positive pin. Okay, but now let's talk about batteries in series, because I think this will help sort of shed some light on the concept. Now, if we connect two batteries in series, we get an 18-volt supply, meaning that this point is 18 volts higher than ground, which we're calling this terminal. Alternatively, we can set the middle point, though, to be ground right here, and that means that we have a positive 9-volt supply and a negative 9-volt supply, because this pin is 9 volts higher than ground, and this pin is 9 volts lower than ground. Now, in the end, all these ground connections are the same point, meaning it doesn't matter how many times you see this ground symbol in your circuit. Everything with that symbol is just going to be connected together in the end. So we could redraw some circuit with a lot of ground connections like this to look like this without any ground symbols at all. Now, this wouldn't change anything about the circuit at all, though. Everything is still going to be hooked up exactly the same, and the function of the circuit is still going to be exactly the same. It's going to work the same. So what's the difference? Well, the difference is when we want to test the circuit and see if the output is correct or not by measuring the voltages at some point, we won't know how to do that because we don't know what our reference point is. So we won't know whether our circuit is operating as it's supposed to be operating. Now, for this circuit, it's really simple because this one is just going to be lighting up some LEDs, right? But for a more complicated circuit where there's all sorts of input waveforms and output waveforms, it's going to be really, really difficult to tell whether the circuit is operating correctly if we don't know what our reference point is, because we just won't know how to measure anything. Now, there's a lot more I could talk about, but I promised to keep this video short and simple. I wanted to get into how this works for like the wiring of your house and stuff, because if you look at your outlets, you can see that there's a hot, neutral, and ground wire. There's 3 pins, so not just hot and ground or something. So the way that works is a little bit different, and it's actually really interesting. But I was afraid of this video getting too complicated and too long. But if you guys do want to see that video...
Okay. iPad. So as that showed, any So you want to take away from this a couple things. One is that you always need a reference point. So when you're measuring, as he said in there, it doesn't matter what your circuit kind of looks like, but you need a reference to say, I have 9 volts higher than that reference point. So what we usually say is that ground we put as 0 volts. And that's an easy way to put our reference point. So ground we're going to look at as always at 0 volts. And then we always want to compare that point to another point in the circuit. And the point we're going to look at is what is going to be called a node, which we'll learn about in a second. So when we look at this, you're going to measure from plus to minus. So some of you, hopefully everybody brought your batteries. So if you look on your batteries that you have, you're going to see that there's a plus side and a minus side on the batteries. So if you didn't bring a battery and your neighbor did, please share. And so look at that. So you have a plus side. And a minus side. If you have the 9 volt, you can also see that one of them is marked as the plus side, and then that means that the other side is a negative. So if I was to take the digital multimeter, which we're going to do in a minute, and you put the black wire is going to be that reference point. So you're in your ground, in the multimeter, you're always going to use multimeter. That's going to be your black wire. Okay, we'll get to the multimeter in a minute. So if you measure that, in between that point which you put at ground and your reference point, this is going to be what value does it say on your battery for your AA? Yes. Yours says 1.6 on it? Okay, yeah, so it says on it 1.5. We're going to talk about that in a minute. But when you measure it, it might be 1.6. So when you get brand new batteries, a lot of times they will be higher value, and there's a tolerance kind of between them. So they're not exactly 1.5, which when we measure, you're going to see. They might be even as high as 1.6. They'll go down to 1.4. As they go down, you're going to know, like, this battery is not going to be working as well. And so it's degraded over time, typically when they're under 1.4 for the 1.5 batteries. So with that, though, on this one, it would be about 1.5 volts between that reference point if I put my black wire and my red wire on the top and measure it. Here, it's between this point and this point that is going to be about 9 volt difference between there. So it's a reference point of the negative side to the positive side. That concept is very important to understand. You're going to see different symbols for ground. There's going to be a signal ground, chassis ground, and earth ground. So what these different symbols kind of mean depends on the application that is going on. All of these mean 0 volts. So this is what you treat as 0 volts or ground. So even though they have different symbols, they all mean the same thing. So for a chassis ground, this is where you're going to have a physical device and actually wire a hard wire to its surroundings. So if you are in lab, when you get there for 1235 lab, you're going to see that there is going to be metal around the benches, and all of the equipment is actually tied to that metal piece, and that metal piece then goes to an earth ground. So these are ways of actually getting a better physical ground, which is your earth ground. So on these, you'll have components within a box that then get connected, physically connected, as you can see here, to the metal surrounding the metal of the box it's contained in. And then on the board or components themselves, you will have, usually this is like a PCB board. This will be a ground plane, and that will be considered your negative for your system. So here's a board, And here there's some area on it that doesn't have a common ground, and then you have the area that has common ground. This is to reduce noise, and there's techniques on when do you want to have that and when do you not want to have that, there's a course now, ECE 3960, which does PCB design and talks about these techniques and when would you want to do this and how do you do this and how do you actually lay it out like this. So that's a technical elective option for anybody that sounds interesting to you. Earth ground is literally a physical connection. So this is it's an electrode that is connected to your house somehow, and then it's driven into the ground. Most of the time they do this when they build a foundation of a house. They put the earth ground right there as they're doing the foundation, and then it's cemented in with the foundation, and then every wire is then connected physically to that earth ground in your home, if it was built correctly. If it was built way back when, it may not have earth ground, but it has a reference ground of everywhere on there. So earth ground is a physical location of where somebody mechanically put a rod in the ground and then tied to that all of the wires in your house. And so that one is the earth ground. So those are the differences between those two, earth ground, chassis ground, and then signal ground would be this ground plane where you're talking about the signals and when it's being moved on something such as a PCB board. Signal ground is also usually what you use for a reference point when you might not be tying it to earth ground or to a chassis ground. Again, that's going to be your reference point of 0 volts. Does that make sense? Okay, so takeaways from this. What is the voltage value at ground? Okay. Why do we care about ground? It's all relative to that ground point. If I don't have a 0 point, I don't know what 9 volts really means, or a -9 from that, okay? And again, hopefully that concept was driven home a little bit more as far as when we're talking about positive and negatives, again, it's not the value itself being negative, it's that the battery was flipped for voltage. So that's what a negative means. In comparison to ground, my positive and my minus lead are relative to that one, to 0 volts. So it doesn't mean that it's a negative value, it just means it's 9 volt value with the polarity as far as it was just flipped. Okay? All right, and then negative current, so that was negative voltage. And then negative current means what? Does anybody want to take a stab at that? Go for it. Correct. Thank you. Yes. So if I've labeled this, and say I actually connect this, if I label, well, let me back up 1 second. So symbols of voltage here. So this is representing a 4 volt battery. This is representing a 2 volt battery. And again, that negative and positive is which direction is this battery facing. So it's a location direction of the battery. So with it being positive, that means that the positive side of the battery is facing up. With it positive on the top, it means it's flipped like this in location. So quick thing, if I put batteries and put them onto each other like he kind of showed there, and well, it'd be here, I guess. I don't think I have 2 AA's. Did I bring another AA? No. So on this, however it is, it doesn't matter. It's going to be the same whether I'm this way or this way, right? It's just a matter of orientation. So that is another concept that is a little bit harder to understand, is like, even though I have a bend, and what is showing between these is a wire connection. So this means there's just a connection from the 4 volt to the 2 volt through that wire. So whenever you're seeing this connected like that, those are just wires. What will be this value here? 0 volts, good. Okay. So you have 0 volts here. Oh, back to current, sorry, I skipped that. So if I label this, and for one, this is not gonna work, and I'll go over that in a second. Let me put a resistor in here. So this element is called a resistor. It has squiggly lines. So now I'm not gonna blow up my circuit. On there, say that I know that this is 2 amps. And I actually measure it though with a multimeter, and say I measure here to here, and I put So first back up, what is the polarity on this wire, on this arrow, sorry, for the 2 amps? Do you guys, anyone remember? Where's my positive and negative on that? On the left side of it. And anybody remember what I said, how to remember? So which direction does the current flow? From higher or lower potential? It's easier to remember, like it goes from high to low, right? So thinking about it as far as like height, it would be like, oh, it's if I have height to it, then it's going to flow from the height down. So that's going to go positive to negative. So that's the way to remember the arrow is still going to follow that too. It will go positive to negative. So this will be positive and this side will be negative. So the direction of it, positive to negative, or if you just want to memorize that where the arrow side is will be the negative side. Whichever one of those clicks with you. So if I measure this though, and say I put my black lead, and actually I would have to cut this out, but I put my black and my red lead, wherever the black one is going to be my positive, or my negative. So never mind. I did this wrong. So that would be positive to negative, so it's going to flow in this way. I'm going to measure 2 amps here, right? And if I have, this goes around a corner, but again, this wire is not necessarily in this location. So it's going to still follow, it's just one closed loop was what this is called. So it's going to just follow along every single wire and element the same direction as what I know it to be. So it's going to go around this corner, go through this element, and go around this way to then get to ground. And on this side, it's going to flow around this corner and go around in the same direction as what I know is the positive direction of it. If I go to now measure here, and I actually now measure it this way and put my red wire here and black, what will I measure here?
-4?
So it will stay the same value as this current, but it will be negative, correct. So it would be negative 2 amps. So the current stays the same in a closed loop. So that 2 amps flows through all of the elements. So you have 2 amps going through the 2 volt, 2 amps going through the 4 volt, and 2 amps going through that resistor. And it's all flowing in the same direction as what is that positive one given. So if I measure it differently, I'm going to get that negative. Does that make sense? Seeing some people, yes. Okay, good. All right, so now let's look at voltage of this. Now if I measure, get a different color, I measure here voltage, and I put the red wire, which is going to be positive, and I reference it to ground here, black wire. What do I measure in voltage? I'm seeing some people say it. Say it louder. Not 6, 2. So from here, which is ground, so this wire is all 0 volts here. So all along this, until I hit an element, it's all going to be the same voltage. So everywhere on a wire is the same voltage. So since I already tied that wire to ground, this is going to be 0 volts here. And then I'm going to measure this side of it, and that's going to be a negative to plus of 2 volts. So when I put that red wire on anywhere on that other wire, let me do blue. So anywhere on this blue wire, that is going to measure 2 volts. So everywhere, each of these are called elements, the voltage sources and the resistors. So all the wires in between them is going to be the same voltage. So it doesn't matter if I measure right next to it or if I measure right next to the other battery, everywhere in there is going to be 2 volts. So here, 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 everywhere along there's just 2 volts. So now if I measure from ground of 0, yeah, I can't do this. So never mind, we'll do this next one. Let's go to this one. So here at V3, what am I going to measure? First of all, I guess, where is my reference point? This is a different symbol for the ground, but it's still going to be there at the bottom, 0 volts. What is V3 going to be? Correct, -4. All right, break up into small groups for a second and figure out what V2 and V1 is, and then you can do the poll. So again, introduce yourselves to your neighbors if you don't know your neighbor, and then talk about what those are. So again, find what do you think V1 and V2 are, voltage-wise? Yes. So the current didn't change in the last one. It's just how am I measuring the current in there? So I said that it was given that it was 2 amps flowing in that direction, but when I measured it, what was I measuring? So that was what I was talking about, is what am I measuring? So because I put the leads on, it made it look like the current was actually being measured opposite, which it was, so that was why it was -2 amps. Does that make more sense? Yeah. It depends on what, it has to be, so remember in the video last time, when you had the battery and then you had the balls that were in the tube and they put the tape on there, that symbolized an open circuit, meaning no current could flow. So this example down here, no current can flow in it. So what is your current here? If no current means 0. So this is 0 amps of current flowing through there because it's open. Correct. So if it's not a closed circuit, we call that a dangling wire. So this is just wire. These are just batteries hooked up next to each other. So I can measure voltage, but no current. Correct. There's nowhere for those electrons to move.
How do you determine if you're measuring negative current or positive?
The black and the red leads.
So the black is always correct.
Yep. So this will be your reference point. So this will be negative, and then this will be the positive.
So this, if it's like it's the negative and positive on the battery, why not the positive on the
On the leads that you're measuring with, correct. Yeah. All right, so good question as far as those questions. Does that make more sense now? Okay. All right, so can't have any current when you have an open like this. So current is 0. And then V1. Okay, so then from this, you're going to go from this direction to this one. You're going to have a -4 plus 15, which gives you a plus 11 volts. So that was correct for V2 is 11. And then from there to there, again, you're going to go up by 3 volts. So it's going to be 11 plus 3 for 14 volts. So those are correct answers. Looks like. Okay, great job. Everybody's that's submitted. Looks like you guys are on the same page. So any questions though? Yes.
Sorry, I have one more question.
No.
Really similar to my last question.
Okay.
So when you measured from ground to V3, you got -4.
Yes. So that means that I put the black wire here,
Yep.
and then I put my red wire here.
Yes. And then when you measure V2, you put the black wire on V3 or on ground.
Ground. So still on ground.
Okay.
So if I put my black wire, let me use, well, I'll put it here. Okay, so if I measure from here, this is a good question, black wire, and I put the red wire here, what am I going to measure? That means just from this location, which is here on this wire, I should do it back. So this location of that wire, and then I'm measuring this wire somewhere. So that's going to be my plus here. But that's only the difference between this and this point, which is, correct, I would measure 15 volts between those two. So if I'm measuring from this point to this point, from there to here is 11 volts.
Why is it +11 instead of -19? Measuring from ground to V2.
So as I go from ground to that point, I look at the polarity here, and that is helping me say, well, it's opposite what way I'm measuring, the plus and the minus from my measuring devices. So that gives me a -4 volts. And then in comparison to that, I add on the 15 to ground. So I have to use it as a comparison always from that reference ground point. Is it the positive or negative? So looking at this sign closest to where I'm measuring. Does that make sense?
Yep.
Okay, great questions.
If you were to put the red wire on ground and the black wire on V3, would it show up as positive?
Correct. Yep. That's a good question too, yes. So if I did switch that and actually put the red wire on ground and the black wire above, it would give me a positive 4 volts. Yes. Okay, any other questions? Yes.
Is that being recorded?
Is what?
Is it recorded? Like the whole thing, is it being recorded?
My video
Yeah.
here? Yes.
Oh, okay.
So yes, my lectures will be recorded, and then says, yes, some of this we're going to go through quick, so going back and reviewing is always great. And then they're posted under the Unit 1 overview. There's a table now that has the video from this week, from the day's lecture. Yes.
What happens if I put nano not on the ground, but a little above the ground and then at the top?
So anywhere on that wire is going to be the same voltage. So whether I I physically put the lead on this point, we'll talk about this when we get to the breadboard, but you're going to see on the breadboard when we actually put components in there, you can measure at different places on there because it's the same wire. So it doesn't matter if it's right next to it physically or if it's down again, like through a wire, another location, physical location. So these little concepts make a big difference in understanding, so I really want to make sure this foundation is really solid. The other thing I want to note is, again, these wires in between the voltages, it doesn't matter if it's bent. So these are going to still give me the same voltage at V1. I'm going to still measure plus 14 volts from ground. Here to here, I'm going to measure still minus 4 volts. And then here to here, I'm going to measure, what was that, 11 volts. So it doesn't matter if I have a bend in it. It doesn't matter if it's really long wire, if it's a really short wire. It gets to be a little bit abstract when you're like, okay, these are locations, and it doesn't matter if I'm here at this location or I'm here at this location. They're going to measure the same voltages at those different spots. Okay? All right, so what will I measure here if this is my measuring device of I2 and I'm given that I have 6 amps of current in this circuit? Yes. Great. So this would be negative 6 amps if that was what I was measuring. Okay? All right, and these little boxes just mean they're an element. So elements that you know of so far are the current. So current, we have the symbol, electrical symbol is a circle. It's a wire in a circle. So this is the schematic symbol for current. This means that it fixes the current in the wires. But the voltage can be different, and the voltage is going to be determined by other things that are connected to it. So the battery and the resistors that are in there, it's going to help determine what is the voltage across this. What is the polarity on this one? What will be here on the top and what will be here on the bottom? Great. Positive on the top and negative on the bottom. So that will be the label of polarity on that. So this will be fixed at some value, 2 amps, 1 amp. It will be given to you, and then it fixes that wire to have that current in the wire that it's connected to. All right, the notation is what I mean by what you're going to see in the circuit. So here the notation is we use that wire, the arrow, and again it's plus to negative. The variable we use is I, or it could be a capital I. They both mean current. Anybody remember the units for current? Good. Amps, and that's an A is the abbreviation for that. So amperes or amps and then A. So that's one element that you now know. And the other element you know is the voltage source. And so the voltage source, I'm going to typically use a circle with the plus and minus to denote the polarity of that. What direction will the current flow here? Down or up? Well, I guess that's kind of a trick question. It could go around, or it can go to positive to negative. So it's going to be the same. Plus to negative would be what you would have as your current. And then the voltage is going to fix the voltage. And the current will vary. Oh, sorry, this is varies. And then current varies. The notation is that we have a plus and a minus, meaning that that's a voltage difference between the two locations. If I only have a plus, assume it's referring to ground. So there'll be sometimes that we'll just have a variable in your circuit on a wire, just like you saw before, it said V2. V1, V2, and V3. That's assuming that it is referencing it to ground. So that's also, just assume that if it's not labeled physically as a plus and a minus in your circuit. The variable is V, and your units is volts, which is V also. So they're both going to be V. All right, the new one that we're going to talk about is called the resistor. And it's a little squiggly line like this. And as you're going to see as you measure these, it doesn't matter which direction you have the resistor. There's not a polarity on it until you have a voltage. So it does have voltage and current that go through it though. Voltage across it and current through it. So as you notice here, every element has a voltage across it and a current going through it. If it's not labeled, you have to assume it's an unknown variable. So for the voltage source, if I put, say, this is 9 volts, then I have an unknown information of current going through it, and that's going to depend on what else is connected to it. For the voltage, or for the current source, say this is 1 amp, I'm also going to have some voltage across it that I would then could label as an unknown variable like Vx, for example. So that's another important concept, is every element has a voltage and a current to it. The notation for a resistor is R. Well, that's the variable, sorry. The symbol in the notation is the same. So you're going to have a little squiggly line in between wires. And then anybody remember the units for resistance? Ohms. So that's your fun Greek symbol that you got to use for ohms. All right, any questions so far? You guys ready to do some measurements? So the digital multimeter, I'm not going to go through all of this, so if you want to read it, you can look online and read it more. What you're going to do is break up into groups again, and then each one of you is going to pick a resistor, and you don't need to know what it is. Or sorry, the batteries. We're going to do batteries first. So go ahead and put the black lead on one side, the red lead on the other, and measure them. So in your group, if you don't have a digital multimeter, please raise your hand. We have some that we're letting you guys borrow today. So go ahead and raise your hand if you don't have digital multimeter and want to borrow one. All right, keep your hands up, and the TA is going to bring around the digital multimeters to you guys. So go ahead and measure the voltage battery first. And if you didn't bring a battery, please share with your neighbor just to kind of play around with it a little. So go ahead and measure by setting the this up. Multimeter, there's going to be a setting for voltage. So you can see on mine, there's a wire above it or a line, that means that it's a fixed voltage in the DC, which is what you want to use to measure. The other one just means an AC, which is an alternating current one. So you're gonna turn it to the voltage, and then you're gonna take the black and the red leads and put them on your battery. If I can figure out how to get this to work. There we go. Okay. All right, so putting the negative on the negative side and then the positive on the other side. And you got to be a little tricky to get this to measure. And then you can see mine says it did for a second. So mine says 1.679. So take a note about what yours says. So you can see it's not exact. The cheaper multimeters are going to be less accurate. So just note that, but they're handy to use. So if you want the cheapest one, it's going to probably be at Harbor Freight if you didn't purchase one yet. Those are like $7. Do get 2 of them though. So note on this, when I turn this around, I should measure what? Negative. So play around with these. And then you can see the negative is right above. Well, maybe you can't see it on mine. So go ahead and make sure you kind of measure both of those. And then also make sure when you're done that you turn it off, because the batteries do die quickly. So the stockroom has a really nice DMM. So the flukes that they have are really like commercial level for $80. But I know they're expensive, so if you don't want to buy one yet, getting that Harbor Freight one, it's really good. Okay, so after you've measured them, talk with your neighbor as far as what did they measure, and then what happens when you flip those leads around. So just take a second to chat about that. Yes, questions? Okay, so hopefully you guys have been able to explore this a little bit, seeing that yes, there is some differences in measurements. Anybody have any thoughts why there's differences? Yeah, so instead of 1.5, mine measured 1.67. Okay, so multimeters are going to make a little difference. The higher quality one is going to be more accurate. Even if I have the highest quality one, there's still going to be some differences. Why? So the physical battery themselves, so the way they make them, so maybe one batch might be all the same, but then the next batch might be a little bit different. So there's always, when you make something physically, there's always going to be some variation and tolerance and differences to it. So that's a whole side of engineering also, is looking at how to make yields be very similar in quality, and so that similarity is there to be as accurate as possible, especially when you get into small integrated circuit chips. So the Lehigh Foundry down there, that's one area you can go into with semiconductor physics. All right, any other comments anybody wants to share from what they learned from this little exercise? Okay, so hopefully it was fun. So resistance itself, one way of, as far as kind of thinking about an analogy, is like thinking about electrical current as water, electrical voltage as the height of water in a pipe. And so when I don't have any good examples, but when I have, a pipe and it's just sitting flat, there's no real force that's making the water flow. If I tip it like this, I raise one height, that's what I think of as like voltage. So from the reference level to a raised level would be my voltage. And so that gives it force to create the current to flow or water to flow in a pipe. Resistance is easy to think about then as the section of pipe and how big it is or how small it is, and literally resisting. So is it creating some resistance for that water to flow? So it is a physical device that is made of material inside. This is actually inside it. It's the ones that you're going to have in your kits are going to be a carbon composite, and they're going to be very cheap. So that difference in them is quite big. So a lot of times it could be even 10% difference from what you assume the actual resistor is. And then it is how it actually creates resistance is based on the material that it is using. So you have different material that is resistive, and so conductivity is related to resistance or resistivity as 1 over the other one. So the units of these, you have in conductivity, you have what's called a Siemens. And Siemens is 1 over ohms. So again, that's 1 over that resistance. And you're going to see that here and there. And then M is for meters. And then resistivity, we describe because it's 1 over, it's going to be ohms times the length. So if we wanted to find out how much resistance you have in a piece of material, it could be really anything that has some conductivity to it, then you would take the length of it, the cross section of it, so the area of it, and then it would be that length as a proportion of the area, and then you multiply it by either the resistivity or 1 over the conductivity. and that's going to tell you how much resistance. You can make resistors out of a lot of different things. So there's a fun little video that in the notes, if you want to go look, he makes a homemade resistor. And so you can kind of go look at that if you have interest in that. There is another thing called a potentiometer. And what a potentiometer is it has 3 different wires on it. And then depending on how you're turning the internal material, it has a little knob on it. And so as you turn that material, it creates more or less resistance. So you can actually get a variable resistance from what these are called, these potentiometers. So, kind of running short on time. So I'm going to leave it to you guys to kind of go look back at this example. The only thing I want you to kind of take away from this example is really that different materials have different resistivities, and they're also temperature dependent. So as you work in harsh environments, space would be an example of that, or if you're working in extreme temperature locations, you want to be aware of every electrical device that you design with is going to have some sensitivity to temperature too. So resistors are not immune to that. So just those are the 2 takeaways I really want you to get from this little exercise. So just go through it. You are going to have a attendance question on this one. So all you need to know is that if you're given the length, given the type of wire that you have, it will give you the diameter, and you can figure out the area of it, and then from there you can figure out the resistivity, or if you're given the resistivity, you can figure out what the resistance is from it. So it's really just hopefully straightforward to plug and play with a formula. So you don't need to memorize this formula, but just more understanding of how the resistor works. What I do want you to focus on is being able to take a resistor, identify what value it has, and then understanding, like, if you don't know what it is, how can you use the digital multimeter to measure it? So that's what we're going to do next, is each one of you is going to take a resistor and then measure that resistance. So on the digital multimeter, there's going to be an ohms setting, and so you'll want to turn it to the ohm setting to do that. To read, right before we do that, to read these, you look at where the last band color is. So as you take out those resistors, you're going to identify on one side of them, it's going to have a flashier color, so like silver or gold. And that will tell you the orientation of how you're going to read the resistor. You're then going to look at the band colors. And the first band color is going to be here. So this is that shiny one. The second band color, and then it's the multiplier. So in this table, brown is 1, black is 0, so this would be 10, and then it's multiplied by red is 2, so it would be 10 raised to this 10 squared, which gives you 100 times 10, so this would be a 1,000 ohm resistor. In this one here, your band would be brown, which is 1. This is supposed to be red as 2, and then green, which is 5. So as I write out the zeros, 1, 2, 3, 4, 5. Sorry. 1, 2, 3. So it would be, 1, 2, 3, 4, 5. So 1.2 meg, or you could say 1,200 kilo ohms. So you put out the zeros and then you put the number in front of it. Okay? So go ahead and work again in groups. Identify one resistor, and then your teammate will get another one and then measure it, talk about it. Identify what value it is and then what you measure. Yes. Okay, so good takeaways. Somebody commented that it didn't matter the direction of the resistor, so it doesn't have a positive and negative to it, which is a good takeaway from this. Some other people thought, this is an example. I thought it was going to be 10K and I measured 9.88K. So again, it's not going to be exact. It has a variation to it. So that's another good takeaway. So yeah, those are great takeaways from this.
Can you go back, please? I was just.
Oh, sorry. Yeah. There we go. Okay, so you should be able to add, if you haven't added to this yet, feel free to add additional takeaways to this. The next section of material, we're going to talk about the breadboard, which we didn't have time to talk about today. So on Friday, we're going to address the breadboard, and then we're going to complete the other topics. So we're going to talk about nodes and Ohm's law, KVL, KCL, and now looking at a circuit and how do we analyze the circuit for these currents and voltages. So if you didn't have your kit today, please make sure to purchase the kit so you have those components and breadboard with you on Friday. If you can, also try to purchase a digital multimeter. If not, I'll still be bringing them Friday. Next week, I won't have digital multimeters anymore to just borrow. If you borrowed a digital multimeter, please make sure to give it back to the TAs at the back of the classroom before you leave. Thank you.